Okay. All righty. Well, I have gotten some grading done, almost to where I need to be. So you get midterm grades next week, and typically I like to have the first 4 modules on the midterm grades. Almost there. I've started on Module 3 projects. So you have grades for Module 2 now. They were, generally speaking, very good. Usually that one is. This next one with Module 3, they'll probably drop a bit. They won't be horrible, I don't think, but they will probably be a bit lower. Let's see. So quiz 4, I just, when all is said and done, I only, well, no, I need to be clear. This class used to take a great deal of preparation time. Now it doesn't so much, but I think I've mentioned I got asked this summer, kind of late in the game, to take over another class, and that takes a great deal of preparation time, and so what kind of happens is I have to go between being kind of creative and grading, and various things have to give way, is what I've found when they have asked me to do too much, or I've said yes to doing too much, or something like that. So quiz 4, it just kind of didn't happen. So what I did was, if you haven't noticed, I put in 20 out of 20 for quiz 4 if you are up to date on your quizzes, which is most everyone. So, but I put that in. If you were not up to date on quizzes, there's no score, but it's not a 0. I mean, that would be rude, right? Put a fake score of 0 in, right? That'd be terrible. And so that quiz, 20 out of 20, as long as you're up on all your quizzes. And other than that, everything's kind of there, so I should be able to get caught up. I'm hoping to get through Project 3 today, and we'll see where Project 4 comes in. I've got 3 days to work on that. And because again, midterm grades go out Monday. And I'll also try to get a quiz 5 up for you in the meantime. And I think that should be relatively simple to do that. But okay, so that's where we are on all that stuff. Any questions on the material? Anything right now? No? Okay. All right. Well, so again, we're in Chapter 4. And so last week we kind of introduced the idea. We were looking at numerical data, and you might have something where I like to use for the numerical data just like crop yield, corn yield or something like that. So you might have a yield, some number of bushels per acre or whatever, and 100, 200, 160, 140, so on. And in this case, what we looked at was just the question of, well, could we find a mean for this and give a confidence interval for it? So that's what we did. We talked about that last week. And then we also asked, well, if I'd like to compare this to some known mean or something like that, I could ask, here are my yields for a bunch of different fields. It's kind of nice, it rhymes. I could ask, well, how does that compare to a typical year, or whatever that means, so over the last 100 years or something, how does that yield compared? And we looked at that. Now what we go to is, what if we have more columns? So, here, our yield is a response variable, but but there's not really any explanatory variable here, right? We just have a single set of data. But I could be asking again about, say, a fertilizer or something like that. And, so this could be a yield 1 and a yield 2, or, something along those lines. And maybe this is 150, 220, 150, 170, and so forth. Now, we're going to look at analysis of variance in a moment. And if we have a problem like this, where our one variable is just yield, right? So our response variable is the yield of the area or the field or something like that. But then why 2 columns? Oh, because we've got some sort of explanatory variable. Now, what's that explanatory variable? Well, could be lots of things. So, for instance, fertilizer type. Maybe this is no fertilizer, and this is my fertilizer of some kind. And so I just want to know, well, how do things compare? Well, if these columns are independent of each other in the sense of rows, actually. So this is we're using 2 meanings for independence. Well, that's really one meaning, but we're using independence in 2 places. So one place is just the general notion of when I compare one variable to another and I want to know, is there an association of some kind? Is there a dependency of some kind? Okay, so that's always kind of in the background of all this because it's what we're trying to do. But another way we could have a dependency here is that just going into it, I know there's a dependency. So the yield 1 and yield 2. Why, I said, well, maybe this is no fertilizer, this is fertilizer. Oh, okay. But it could also be one year and a different year. So see, this could be the same field in each row. Field 1, field 2, field 3, field 4. Now, if they're the same field, and maybe this was yield 1, and that was last year, and now this is current year, okay, if that's what's going on, well, heck yes, there's a dependency through this row between those 2 numbers, right? Because they're the same field. A much more obvious example would be if we went through and were asking about individuals' heights, and we took each of your heights in, say, when you were 10, and then again when you were 11. Well, your height is very much attached to you. There's a common denominator there of you. And so if these are the same fields, right, for all I know, this field is full of rocks. This field has a lot of shade. This field doesn't get much water. This field, right? They're maybe all a bit different. Maybe they're similar, but definitely I would expect these two numbers to be quite similar because they're from the same field. Okay? I expect a dependency there in that sense. If that's the case, if we can pair our data in the rows, if they're paired, okay, so paired data like this, what we end up doing is we actually transform it, okay, transform by subtracting one column from the other. And so, in a case like this, if we were asking, null hypothesis for something like this, we'd look at the two means and we might ask, is the average in yield 1 equal to the average in yield 2, right? That would be our null hypothesis. And another way to state that same mathematical relationship is y1 minus y2 equal to 0. Well, that, in this particular case, for paired data, now it's very important, we only do this with paired data, but for paired data, we actually do this subtraction line by line. Okay, so we would create a new yield that was, say, and it doesn't really matter which way I go. Let's say I do it as y1 minus y2, 100 minus 150, 200 minus 220. Okay, that is my new data set that I will use the same techniques, so 160 minus 150 and 140 minus 170 and on down like that. So I will create a new column that is that subtraction of those paired data and analyze that using the same technique I use on a single column, because now it is a single column. And so for this subtraction, I would be looking at that null hypothesis, and of course the alternate is that it's not equal to 0. I left the alternate out of this thing, so HA y bar minus, not equal to y2, and y1 minus y2 equals 0. Okay, so I would turn this hypothesis into that one and just evaluate it that way. Any questions about that idea? Yes?
So like would this be like for like our pilot project, we're trying to see if there's like a difference in the two like data sets, so would this be appropriate to use in analyzing that data?
Okay, so yeah, you want to know if there's basically you have two categories. So in your final project right now, you're thinking that your one variable would simply be two categories, and you're checking, is there a difference? Well, the question becomes, is each row coming from the same source? No. So in that case, they are not paired. Okay, so they would be unpaired data, and you'll use, well, most likely you would use, at least under this specific situation, an analysis of variance that we're going to look at in a minute. Okay, yeah. So good question. You know, it's a matter of, can I put them together? So, you know, another example might be something like movie ratings, right? And you could have something that looks like the same sort of data, but in one case you would pair it and do this subtraction, and the other you wouldn't. And so, you know, you could look at movie ratings, and you know, you could have a data set where you got male and female, and you know, who knows, you know, something out of 10 or whatever, and you ask a bunch of males and females, you know, their ratings of a particular movie, and you know, maybe that 10 and a 9 and a 3 and a 5 there, and a 4 and a 7 and a 7 and a 7, and you know, and you could have data like that. Well, this data might be paired, it might not. One of the questions would be, well, who are these males and females? So for instance, if I just got on the web and could somehow go to Netflix users, and I made sure I got a random sample of Netflix customers, something like that, and you know, but I just kept track of whether they were male or female, then I would say these are not paired data. On the other hand, if anybody going to movies these days? Can we? I don't know. I haven't gone to many movies in the last few years, so you know, it doesn't really matter much to me. But you know, so suppose it was date night, Valentine's at the movie theater, right? And you ask couples coming out of the movie theater to rate the movie. Oh, well, then all of a sudden, I would say these are probably paired, because this might be couple 1. This might be couple 2. So see that the data all of a sudden have a similar source in each row.
So if there's like a relationship
between this one and that one. You know, and that's where using like people and saying, oh, a relationship. So, you know, it could be siblings, it could be just relatives, you know, it could be all sorts of different things. But it's, yeah, if there's if you feel there's an underlying relationship between that data point and that data point because of how they were gathered, oh, then you should probably be thinking they are dependent in that way. They are not, it's really about observations. These are not independent observations, right? If I ask a couple, then that observation is very, very much linked to that one. Now, they may have nothing to do with each other, but they are very linked, you know, and so we should probably do a subtraction in that case. Now, If you go to 3 columns and there's still that link, actually, I don't know what the heck you do. Right? Because you'd really want to talk about subtracting all 3, right? You know, but, well, no, it doesn't work that same way. And so I've never really looked at that, nor do I ever remember that coming up in a course. My best guess is the answer is statisticians might be saying, we don't know how to handle it, don't do it. So I don't know. Okay, so, well, the one exception, you could go with like a pre-test, a mid-term test, and a final test, right? In that case, but then probably what you would do is you'd look at these 2 and do a subtraction, and you'd look at those 2 and do a subtraction, something like that. But that's a very special case. Okay, other questions? Nope. Okay. All right. So let's go on. You know, if they're not paired, if they are independent observations, then what we want to use is an analysis of variance. Now, your textbook, it talks about the difference of 2 means with independent observations. Okay? We don't care. I mean, it's a perfectly fine thing. It's the t-test and all that is what they call it for unpaired data. But we can do it with an analysis of variance table, and we get exactly the same p-value. And so since we get the exact same p-value, why make 2 different templates? Right? I can put my data into the analysis of variance template and it'll work just fine. So that is what we'll do in this class. Okay, so what we want to do is with this analysis of variance, and people write ANOVA for short. We'll just look at 3 columns. And so we're given K groups, treatments, categories, something, whatever you want to call them. Now, your textbook tends to go with groups, so I'll try to use that a lot. Most things I ever see, it's called treatments, but very generically, they're categories. So any of those words work. And in our case, we're going to have K be 3, so K is the number of these groups or treatments or categories. And so we'll have group A, group B, group C, and we'll have data, so an A1 and A2, and we'll have some A sub n A. Now I put the little a on it because each column does not have to have the same number. B1, B2, same thing there, B and B, and C1, C2, on the C and C. Okay, so I have 3 columns of data in this case. I could have 100 columns. Now, something's probably wrong if you have that many. I mean, you need a different experiment, I think. But you could do that. And so what we're going to do, and all this does, okay, it creates a numeric value that then we can match up with a particular statistical distribution called the F distribution, which is not in the back of your book. So the back of your book has the normal distribution, the t distribution, and the chi-square distribution. It doesn't have the F distribution in there. But it gets, it looks at that F distribution and produces a probability, which is our p-value. Okay, so just like in chapter 3, we're asking, given we assume our null hypothesis, which we'll look at in a minute, but assuming our null hypothesis, what is the probability of getting these kinds of data? And if that probability is tiny, we'll assume our null hypothesis is not correct, right? We'll reject our null hypothesis. If that probability is big, bigger than 0.05, we'll not have enough evidence to reject that null hypothesis, so we're stuck with it, unless we go get more data or something like that. Okay? So how, what are we actually doing to do that? Well, we're going to check how the variance, okay, so the dispersion in means between groups, okay, or treatments, whatever we want to call them. Okay, so we want to check this. So this is sort of a big, very long sentence that involves some formula stuff here. Okay, so that variance. Well, we're going to get at that variance through something called the sum of squares. So here I've got sum of squares groups. Okay, so G for groups, sum of squares groups. And for this case where we just have, the 3 columns, and I didn't, I didn't write down, we can get the mean A bar, B bar. Now I noticed on Tuesday, when I said B bar, it made me think of Justin Bieber. And I was trying to figure out, are you all like too old or too young for Justin Bieber, or just right, but nobody wants to admit they're a fan or something like that? I don't know. It's kind of an interesting character because I've sort of gotten the feeling that people don't want to admit being a Justin Bieber fan, yet there may be lots and lots of them. So I don't know. But anyway, so we've got A bar, B bar, and C bar, the averages of those things. And so what we're going to do is we're going to check this variance between those means. And so we've got the NA here, so that's the number of data there. Now, this is just here because these don't have to be the same. Well, it'd kind of be there anyway, but they don't have to be the same. So suppose I had 10 data points here, but 100 data points there. Well, even if the average distance that we're going to write here is about the same, this would far outweigh that when I just add them, if I added them each up. But if I only take A bar minus the overall mean and C bar minus the overall mean, it looks like they mean the same. But yet there were a whole lot more data here. So I need to reflect that. I need to get a weighted average. And so I multiply by that number n, And I take that difference squared. Okay, plus n sub b b bar minus x squared. Now again, this x bar here, that is my overall mean of all of those data. Okay, so I'm just checking, okay, I can take the mean of all of my data. How does the mean here compare with the mean there as far as being separate from the overall average of everything? Okay, and then of course my last column, so n sub c, c bar minus x bar squared. Now, actually all I have to do to turn that into a real live variance, and variance, what the heck is variance again? Right? It's just the square of the standard deviation. So this is the first step to finding a standard deviation. Right? I have three numbers, a bar, b bar, c bar. And I find their difference with the overall mean. I square it. But this is accounting for how many data I have. So, you know, if I had 10 data items, well, there'd be 10 of those. 15 data items here, well, there'd be 15 of these, and so forth. So it's weighting it. But so I add those differences up, and then I divide by n minus 1, where n, that n, just a generic n, is all my data. Okay? And that would be a real life variance. Okay, we aren't there yet. We just call this the sum of squares group, and never do we call anything actually a variance. It's kind of a weird thing with this, but we'll find it, but we don't call it that. And if we then just took the square root, that would be a standard deviation. So this is not new, right? We're looking at the dispersion of those means. How far apart are they from the overall mean? Okay? So we're just looking at that, and so we want to compare that. So we want to check how the variance in means between group treatments, this thing, compares with the variance, and maybe you're now seeing why this is called analysis of variance, the variance within groups or treatments. Now, and we don't actually use this particular computational formula. We will use this. This is in our template, but we don't use this next one. We could, it's just not the way it's usually done. And so we call this sum of square errors or residuals. So sometimes you'll see it SSE, sometimes you'll see it SSR for residuals. It's what's left over from this. So that's why it's called residuals sometimes. And what we do here is we get this same idea of variance, but now we're, as I say, we're looking within each treatment or group. So I want to see how A1 differs from its mean for that group, plus A2, and how it differs from that mean. And we'll go all the way to A sub n, A minus A bar squared, plus B1 minus b bar squared, b2 minus b bar squared, all the way to b sub nb minus b bar squared, and then plus c1 minus c bar squared plus c2 minus c bar squared, all the way out to cnc minus c bar squared. Okay, so again, see what we're doing is we're looking in each column what its variance is. Right? So we're looking at the variance here in that column, this one, and this one, we're just adding those all together. Okay? So that's what we want to do. We want to compare that difference with that difference. And what we know statistically, so statisticians, under the right assumptions, these are independent observations. The underlying distributions are normal distributions. Some, things like that. If that's the case, then if these three means, or however many we're analyzing, if those are all equal, then it turns out that SSG over K minus 1. Yeah, I misspoke back here. I think I said divided by N minus 1. I misspoke, sorry. It's K, the number of groups. Okay, that is equal to sum of squares error over N minus K, where that N is the number of data total. So all those three columns in our case added together. Yes?
K is each of the groups.
Is how many groups?
And then
Yep.
N is the number of observations.
Total number of observations that you see in the data.
Okay.
Yep. Yeah, so for us, this K would be 3 for this example I'm using here. And then that uppercase N, I don't know what it would be, but it would be the N sub A plus the N sub B plus the N sub C. So, okay, but those would be equal. If this is true, those turn out to be the same number. Okay, and when you think about it, and here's where box plots come in handy for these type of data, is that, here's A, here's B, here's C. Well, suppose, I do box plots for these data. And they look kind of like that. I could put a median in there. Now, if it's nice data and symmetric and so forth, these medians will be very close to the means. Right? But if those were my data, yeah, they all look the same. Right? And what we would notice is that the overall mean, from taking the average of this, the average of, all those added together to get the average, right? They look all about the same. So when I look at that, that's not going to be a whole lot different. Well, it's going to be a very small number compared to any variation that goes this way in a given column. And so what they end up looking for, right? If under these nice circumstances, these ought to be equal, then if I divide that by that, I ought to get 1. And that's kind of what we're looking for. And if this starts getting too big, much bigger than this, that's when our picture, so here the picture would look a lot like that, like the means are all equal. But, imagine you have instead your data have box plots that look something like this. Then as you look at that, when I start looking at this number, it's going to get a lot bigger. Okay, this number here, when things are like this, is going to get much bigger. This number isn't going to grow so much because, again, this number here is just based on that. Well, those didn't change much, right? They look pretty much like these. They're just in a different position now. And by raising and lowering these, that number gets bigger. Okay? Because, again, this number was that mean. Now, I'm pointing at it like it's a mean. It's really a median, but, don't wreck a good story with facts. So, this mean, its difference between the overall mean, well, I'm not sure where the overall mean is, but maybe it's in there somewhere. Just like here, the overall mean was maybe in there somewhere. Well, see, these differences are small. These differences are big. Well, that one's not so big, but... Okay, so they've gotten bigger, so that makes this much bigger. And so when you see data that look like this number is going to be much bigger compared to that number. And that's what we're going to look at. We're going to look at the ratio of this number divided by that number. And if it's way bigger than 1, it probably means, our means are actually different. Okay? We will reject this idea. Questions about that? Okay? We're looking to reject this idea. Okay. So that's what's going on. Now, when we make the table, the table in many ways is really pretty simple. It tends to freak a lot of people out, but there's not much to it. You just have to get the calculation started. And the reason for the table is simply to organize yourself so you get the numbers in the right place. So here's the thing you're making in your template, this ANOVA table. You're going to have a row for treatments or groups. You're going to have a row for error. And you're going to have a row for total. Now, it's not a row that's truly needed. Because we could calculate this straight out. Again, it's just not the way it's usually done. And so we'll do it the way everybody else does it. And so we have a first column that is our sum of squares. And you will actually calculate that, sum of squares groups. And again, not in a spreadsheet, not that hard to calculate because it'll do it, the spreadsheet will do the averages for you and do the counts for you and so forth. So not that difficult. I mean, you got to look at the commands and so forth, but not that bad. Then we'll also compute this one, the sum of squares total. And this is the only reason to really have it in the table is we'll calculate those two, and then we're going to make this one the sum of squares error by just taking the sum of squares total minus the sum of squares group. So we'll just fill in that spot by taking that minus that. So we won't, we calculate it, but I mean, it's not from the definition, it's just from these two. Then we need our degrees of freedom, and that was our k minus 1 that we saw in that formula before. This one down here is going to be n minus 1. And then this one is the n minus k. Again, you can get it, so it's just n minus k, and you could, I don't even remember now on the project how I tell you to get it, if I just tell you to do that, or the other place it can come from is, if you take n minus 1 and you subtract k minus 1, well, that's what you get is n minus k. So I think we do it this way. We actually just take that number and do a subtraction. Okay? So that's degrees of freedom. Then this is what I would actually call the variance, but they call these mean square errors and mean square groups. So I'll call it mean. And that is the SSG, the sum of squares groups, over the k minus 1. Okay, so we'll just do that division with those cells. And then the mean squared error, and that's sum of squares error over n minus k. So those are the two things that are supposed to be equal. And so the final portion of the table as far as our calculation is to create the F statistic that will have the spreadsheet evaluate for us. Now, it takes 2 degrees of freedom, and it's really important that they're in the right order. Because if you swap those two things, you get a different answer. Okay, so it's this top one, and then the bottom one is the order for the degrees of freedom. And this value is just the MSG mean squared groups divided by the mean squared error. And that's the number that if the means do appear to be equal, that should be about 1. And if they seem very, very different, I would expect that to be a big number. Now, what's a big number? A lot depends on n. Right? So if n is huge, a big number, I don't know, might be 5 or 6. If n is small, a big number might need to be like 15 or something like that. So it's all in here when you look that stuff up. But that's the analysis of variance table. So the big deal in calculating it really is, you have to get that and you have to get that, which takes a little bit of effort in the spreadsheet, but it's not terrible. But those you have to calculate. And then after that, these aren't so bad to get. I mean, we'll automate it in the template, but in the end, I could look at the number of columns and do the subtraction, put that in. I could get this count pretty easily. But see, once I've calculated those two things, that subtraction's easy. It's not too bad to get those. And then you can just do the subtraction there. And these are just division, these three are just divisions of what information's already there. And then, of course, we have to look that up to get a p-value. But, what we're looking at then is, our null hypothesis H0 is that for all our different categories, you know, x1 bar equals x2 bar equals up to xk bar. And our alternate is at least one is different. At least one xi bar is different. But then that's similar to saying if the categories are just different levels or different categories of a big categorical variable, again, going back to the fertilizer, right? I could have different categories of fertilizer. So my question is, is yield associated with fertilizer type? And, well, if I fail to reject H0, no, it's not associated with it. They're independent. Because again, as here are columns of data. As I look down each column of data, it doesn't matter which column of data I'm in. I get pretty much the same numbers. Independent. But if that column of data has numbers that are much, much bigger or much, much smaller than the rest, well then there is a dependency because it matters which column I'm in. Okay, so independent, dependent. Same thing we had with chi-square, right? Chi-square, the idea was all the proportions were similar between the variables, and at least one of the proportions was different. Okay, and again, they were independent and dependent. So each time our null hypothesis, when we're comparing two variables, null hypothesis is they're independent, and the alternate is there is a dependency, some sort of association going on there. Okay. All right, well, that gets us to the end of that. Now, Tuesday, I talked a little bit about Bonferroni corrections. So that class, I don't know if I put that class up on there yet, but at the end of that, I talk a bit about Bonferroni corrections. And if I can get any other videos up, I'll do that as far as some of these ideas. Okie doke, and I will see you next Thursday.